So here's worked out example number 1 on your second handout. Keep the first handout right next to you while you do this problem with me, and you'll see that the 2 proportion z-test feels a lot like the 1 proportion z-test. Just carry them all out the same way. In a medical study, 300 volunteers with a certain medical condition were randomly placed into 2 groups. 200 were given a new drug, and 130 of them responded positively to the new drug. Okay, 100 patients were given a placebo and 50 responded positively. Is there evidence at the 0.01 significance level that the new drug is better than the placebo? Okay, so I could say this for the state phase. Let P subscript drug, D for drug, equal the percent that are on the drug who responded positively, and let P subscript P, P for placebo, equal the percent on placebo who responded positively. So not that bad. You just have 2 parameters to define because you're comparing 2 populations to one another. Okay? And then the null hypothesis is the percentage on the drug is equal to the percentage on the placebo. Or you'll probably see me when I get back tomorrow saying PD minus PP, equals 0, which is just another way of saying they're equal, but I like to have a number in my hypotheses. The alternative hypothesis is, so it says, is there evidence that the new drug is more effective? So then we can say PD greater than P subscript P for placebo, or I can say PD minus P subscript P is greater than 0. And that's basically just algebraically subtracting P subscript P from both sides of the first way. So I prefer these. I'll explain when I get back. Okay. So that's the state phase. Not too different. Okay, plan. Now here's the one that gets a little bit long-winded because you have to check the conditions for both samples. So we can say, well, let's see. First of all, they were randomly placed into the 2 treatments. They were not randomly chosen, they were randomly placed. Now, in future problems, they were randomly chosen for something, but here you want to say that they were randomly placed into the 2 treatments. Okay, let's see, the 10% rule. Let's see, there's a total of 500 patients who were involved in this study. So I don't have to necessarily talk about, each one separately. I can just kind of combine the 2 this time. It won't always be the case, and say 500 patients with this condition is likely less than 10% of all patients with that condition. So something like that. So I've got the randomness and 10% conditions checked. Now, usually for the expected number of successes or failures, sometimes I write, sometimes I make a table. So I'll just say this. So let's see, the new drug is more effective. Let's see, so how do I state how many people were expected to respond positively. Well, if the null hypothesis is that they're equal, then would I have expected 50% to respond positively in both treatments? So I can say something like this. If the null hypothesis is, that the difference is 0, then I would have expected the number of positive responses in the drug group to be half of them. So 50, oh man, I totally messed up earlier. It's a total of 300 patients. They were divided into two groups of 200 and 100. Okay, sorry about that. You can fix that easily, though. All right. Let's see. 50% of 200 who received the new drug is 100, and the expected number to not positively respond in the drug group is the other 100. Okay. You'll see that you calculate the expected values, roughly the same way. And then you have to just say the same thing for the placebo group. The expected number to positively respond to the placebo would be half of them, and 100 we're given the placebo is 50, and the expected number to not positively respond to the placebo is also 50. So you can see all four of those numbers are greater than or equal to 10. So the conditions for a 2 proportion z-test are met. Okay, so there's the plan phase. It's twice the writing. You got to check the 4 conditions for both groups. Okay, now we're moving on to the do phase. The first thing you want to do is calculate both of your p-hats. So we want to know what p-hat drug and p-hat placebo are equal to. Well, let's see. P-hat drug, 200 patients, 130 of them responded positively. So we want to take 130 divided by 200, and I think that's 65%. So that came from 130 divided by 200. Okay, on the placebo, we had 100 patients and 50 positive responses. So then the placebo p-hat is 0.50, 50%. Okay, so now the next thing that you want to do is you want to subtract those two to get their difference. You're comparing the drug to the placebo, so the way to do that is to subtract them and get the difference. Now, you can subtract them in either order, but what I usually suggest is subtract them in the same order that you stated your hypotheses. So since I stated my hypotheses as drug minus placebo, then I'm going to calculate p-hat drug minus p-hat placebo. Well, that's obviously positive 0.15 if you were to subtract those two numbers. So that's your score. That's going to tell you how different they are or not. Okay? Now, the expected value of p-hat drug minus p-hat placebo is 0. if your null hypothesis is that they're equal to, the difference will be zero, in other words, the two things are equal, then that's what you're always expecting your mean to be. I know it's kind of a weird one, but that's your mean. It's always zero for a 2-prop z-test. Okay, now you got your score, your mean, and you need your standard deviation. But before you can calculate your standard deviation, you have to calculate p hat pooled. And basically all this means is put both groups together. So p hat is x over n, right? So you go back to your data and you get your x's. So you see there's 130 in the drug group and 50 in the placebo group who responded positively. So then that's going to be 130 plus 50. And then do you remember there were 200 in the drug group plus 100 in the placebo group? So that's 180 over 300. And if I grab my calculator and get 180 over 300, then we get 60%. So 60% of everybody involved in the study positively responded. Now, the only reason you need that number is because the standard deviation of p hat pooled is needed. It's the great big old square root. You take p hat pooled times 1 minus that divided by the 200 for the drug group plus the p hat pooled times 1 minus that divided by the other group's size. It's not nearly as bad looking when there are numbers instead of the written words. So let's see, we're going to calculate this. Okay, I just got that to work out 0.06. You may want to practice that to make sure you got the same thing. So there's our standard deviation. So now remember, z is equal to score, which for this problem is the 15% difference, minus the mean. You were expecting the difference to be 0, divided by the standard deviation. So we got 0.15 divided by 0.06. Is a z-score of 2.5. Okay, now you draw your normal curve, and just like any other time you draw a normal curve, you label the middle with the mean, which is 0. Then you put your score, in this case 15%, where it roughly is, and you shade the wing that matches your alternative. Our alternative is greater than. So we're looking for that p-value. Okay, how would we find that p-value? Normal, C, D, F. What would that be? 0.15, infinity, 0, and 0.06, the mean and the standard deviation. Well, I can tell you if you do this, it should basically be 0%, maybe a little bit larger than that. Okay. So what's your conclusion? Since the p-value is less than the alpha level, I reject the null hypothesis. And then say for your second sentence, there's evidence that the drug is better than the placebo. In other words, when you reject the null, you're saying there's evidence in favor of the alternative, which is saying that the drug is greater than the placebo. All right, you should try to work out that second problem for homework tonight.